Hi everyone, this is the third video on log functions. In the first video I introduced you to the basic log function. In the second video we looked at transformations of the log function, and in this video we'll look at a specific log function that has been transformed from the basic log function, and we'll have a look at how to determine the x and y intercept of the transformed log function. Just to remind you what it looks like, the basic log function looks like this. It cuts through the x-axis at 1. So when x equals 1, y equals 0. To the left of that point, we have the graph descending to negative infinity. And from that point to the right, we have the log graph ascending not so rapidly, but it does ascend to positive infinity. So a rapid descension here and a gradual ascension here. And we've talked about the properties of log functions, which makes sense to why it cuts through at x equals 1, why it ascends gradually, and why it descends quickly on the other side, including a vertical asymptote at x equals 0 here. So we've done all that in other videos. That was just a quick reminder where we're at. So for this video, we're going to have a look at this function here, y equals 2 log base 2 x plus 1 minus 3. Now, the log base 2 doesn't really have any impact on what we're drawing here as a sketch. It would have an impact if we were literally graphing it, but as a sketch it doesn't have much of an impact. I've just chosen it to give us a decent sort of curved line. I could have chosen anything to illustrate this. Okay, so just a reminder that this number here in front of the log function is the dilation and reflection factor. So if the number in front there is a fraction, it will cause the graph to incline less steadily. If the number in front of the log function is a whole number, a big whole number, then it will cause the graph to increase more quickly. And if that number is negative, then it will cause the graph to reflect. So in this specific example, we have the number 2. Okay, so the graph will increase a little bit more steadily, and it's positive, which means the graph stays the same orientation, it doesn't reflect. So if I were to draw that, this is just a really quick sketch. So there's the point 1. If the original log function sort of looks like this, like so, then the new function, the two would have this effect, ignoring the rest of the things, like that. Probably more like this, actually. It would still eventually catch up, but a little bit further down there. Okay, so that's basically what the 2 part is doing. I'll just undo all that. Let's leave that basic log function there while we look at the rest. What else have we got? We've got this plus 1 here. Remember, this is a horizontal shift or translation. Okay, and remember we always take the opposite sign. So if it says x plus 1, we're shifting, oops, this camera's a reversey camera, so we're shifting that way. We're shifting to the left 1 unit, and if it was negative, we'd be shifting to the right 1 unit. So it's a horizontal shift left 1 unit. So looking at that in isolation, not looking at it in terms of the 2 and the negative 3, we would be looking at, just by having a horizontal translation of 1, we would be looking at something along the lines of, to the left was it? So something along the lines of like that, with a vertical asymptote now being at -1 instead of being at 0. So that's the effect of the +1. Okay, and that of course leaves this -3 here. We do pay attention to the sign this time. So that's the vertical translation. And because it's negative, it means we have a vertical translation down 3 units. Like so. So kept in isolation, it means that the graph would be, so this point here would be 1, 2, 3 units down. So we would have, that was a terrible graph. That was a terrible line. Let me do that again. So the point that was 1 is now all the way down here. And we would have it climbing like so, with there being an x-intercept here somewhere. Okay, so what we would need to do is first of all have in our mind that there is a rough shape in mind here. So that would be something along the lines of 2 means there's a dilation, but that we probably can't take that into account too much when drawing a sketch. But the +1 and the -3 we can do. It's not reflected. So taking the +1 and the -3, I would probably go from here and say the +1 means it goes back a unit and then goes down 3, 1, 2, 3. And so the graph at -1 being the new vertical asymptote, the graph is going to be sort of like so, roughly. Okay, that's what we're sort of roughly headed towards. But what I'd like to do is I'd like to show you how to find the x and y intercept. This will affect this number here. So that was me putting it down 3 units. Is probably not really terribly accurate, but it just gives me an idea about what I'm looking for with the graph. The fact that it's gone down and to the left is important, I think, when thinking about what it's going to look like. Okay, let's get stuck into it. So let's find the x-intercept first. So the x-intercept is when y equals 0. So that means that, what did we have? We had 2 log base 2. So that means 0 is equal to 2 log base 2. Then we had x plus 1, and then we had -3. So that is our equation which we need to solve. So let's go for it. I might just move everything over to the other side of the equation, so that'll make it 2 log base 3 x plus 1 minus 3 equals 0. Just easier to deal with from there. 2 log base 3 x plus 1 is equal to 3. How did I do that? Added 3 to both sides. Then I'm going to divide by 2. So that gives me log base 3. Oh, it's base 2, isn't it? Sorry. Log base 2 of x plus 1 is equal to 3 on 2. Now I'll leave it there for a second, and I will just say that it's really important to know that you cannot divide by x plus 1, or you can't divide by log base 2, or something funny like that. The x plus 1 in here, this x plus 1 is an input to a log function. So it's tied up with the log function. It's not two separate things. This is just a single number, and whatever that number is determined by what the value of x is. It's not log base 2 times x plus 1 or some other random concept like that. So you can't undo this very easily. So don't, because you don't need to. what do? Well, we just used our basic log idea. I'll write it over here on the side here. Remember that log base AC equals B, if and only if, that means it goes both ways, a to the power of b equals c. That's the definition of a log, right? So we're just going to do that. So the base down here is 2. What takes the role of b? Or the other side does. So it's 2 to the power of 3 halves is equal to c, is equal to x plus 1. Okay, which is good, because that means that x is equal to 2 to the power of 3 halves minus 1. And how did I do that? I subtracted 1 from both sides and then flipped the equation. Okay, so that's good. We can do that. That's just a calculator operation. I know that 2 to the power of 3 halves, by the way, oops, wrong colour. I know that 2 to the power of 3 halves is equal to, well, what have we got? 2 cubed is 8, and then this over 2 means it's a square root. So putting it into square root form, I have the square root of 8 minus 1. And if you rationalise square root of 8, you get 2 root 2. So it's 2 root 2 minus 1. Now, that's how I would expect you to label, and I will do that in a second. That's how I would expect you to label the graph at 2 root 2 minus 1. But you will, of course, need to have an idea about what 2 root 2 minus 1 looks like. So that's when you'd get your calculator up and go 2, and use your square root button, but I'll just have to use SQRT for this one. 2 root 2 minus 1. And so I just want to keep in my head somewhere that 2 root 2 minus 1 is 1.83. So it's really close to 2 without being 2. 1.83. But really, for the exact point, I'm going to write here in brackets 2 root 2 minus 1, comma 0. That's the exact coordinate. Okay, there's the x-intercept done. Now, the y-intercept is the only other thing we have to really worry about. So the y-intercept is when x equals 0. Okay, we can do that. So y is equal to 2 log base 2 of 0, what was it? Plus 1. Minus 3. We can do that. That's equal to 2 log base 2, 1, minus 3, like so. So just looking at the log base 2 of 1 part, just that bit there, what's log base 2 of 1? Well, I'll do it on the side. Log base 2 of 1 equals what? So 2 to the power of what is equal to 1? 2 to the power of 0 is equal to 1. Okay, so log base 2, 1 is 0. So we've got 2 times 0 minus 3, which gives us negative 3. So that's nice and tidy. That's simply 0, comma, negative 3, which is kind of what we'd expect from our translation, really. Okay, we've translated from 0 to negative 3. Okay, so let's put all that together. I'll have to flick between screens to do this, but let's have a look at some axes to start off with. Use your ruler for your axes, of course, as usual. There's my axes, nice and straight. That's the x-intercept, sorry, the x-axis, that's the y-axis. And now we shall just do a quick, just a rough idea. So if I say that's 1, 2, 3, okay, so this point here is going to be 2 root 2 minus 1, 0, there we go. So that's the point it's going to cut through the x-axis. I know there's a vertical asymptote at x equals minus 1, so I'm just using my little divisions there just to keep it roughly to scale. I'll just do the vertical asymptote in red just so it stands out a bit. Again, I'd be using a ruler for this if I was being a good boy. Like so. So there's the vertical asymptote there. And the other thing we know is that it cuts through at the y-intercept is -3. So just sort of roughly drawing a square there. There's -3. So I've labelled my critical points, and now I just need to do my best to sketch that, which is probably going to be a bit dodgy, but here we go. Like so. So it looks something roughly like that. Okay, so that's my sketch done. Might want to put arrows on the end of your blue line. My blue line over here doesn't quite look like as if it's going to flatten out with the vertical asymptote, so I was probably a bit too generous with labelling my numbers out as far out as I did, given the space I had. I probably should have had them in a bit closer. That's the beauty of sketches, that you need to just be a bit careful with that. Okay, so how about we have a look at Desmos. So there's my drawing there, and let's have a look at Desmos, because here's a little something I prepared earlier. I had x as being -1. Sorry, b as being -1, because x minus -1 is x plus 1, which is what our function was. And here it is here. So you can see what it looks like compared to the basic graph there, but you can see the y-intercept is just like we said. It's at 0, -3, cuts through the x-axis at 1.828, which is 2 root 2 minus 1. We saw that before, didn't we? I'll just get it up here, I'll show you. So there you go, see, we worked out that it was 1.83, and there was the graph, the coordinate that we worked out. And yeah, there's the shape of it sort of escalating a little bit bigger than it should be because of the dilation. I probably didn't capture that in my graph, but you know, it's getting there. It's roughly right. My graph is a bit more stretched out than that one there, but we've got the same sort of sense of what's going on. Okay, so that's probably enough talking from me. That's how you go about doing your graph. So just in summary, you consider each part of the transformation and decide what kind of effect it's going to have. That leads you to probably have an idea about what the graph should look like. And then once you've worked out what the graph should look like, you then work out the x-intercept by setting y equal to 0 and using some log rules, and then work out the y-intercept by setting x equal to 0 and using some log rules. And then you can put those points onto your graph and join them up to make your line, and hopefully you do a slightly better job than I would. But it gives us an idea of what it is. Okay, that's it from me. Thanks.